Hi, everyone. Good morning. My name is Hesper. I'm a PhD candidate at University of California, San Diego.
And I'm Sina, a postdoc at MIT.
So we're here today to give a graduate course called Introduction to Geometric Fluid Mechanics. We want to thank Mark and Ruben for organizing this and inviting us here. And you want to thank the audience? You want to thank the audience?
Oh yeah, and also thanks to the SGP conference for hosting this. It's been great. Yeah.
Okay, I guess let's get started.
Yeah.
So first, why should geometric fluid mechanics be a part of SGP? So for starters, fluid dynamics captures many phenomena in the universe. In fact, fluid simulation goes far beyond theoretical science. They help us forecast the hurricanes. They help us study the ocean currents, design aerodynamic vehicles, build optimized cooling systems, and in computer graphics, they let us create believable virtual worlds from volcanic eruptions to swirling smokes and explosions. So these events are mathematically modeled with differential equations such as Euler's equations or Navier-Stokes equations. These are classified as hyperbolic PDEs, and they're considered a little more involved compared with the elliptic PDEs that we're more used to see in geometry processing when we're solving a Poisson problem. So we care about simulating these PDEs accurately and efficiently. It turns out that structure-preserving algorithm can help us achieve that. So in this course, we will show you what the geometric structures that emerges in these physical systems and how are we going to preserve them in our simulations. Okay, so to do that, we need a set of mathematical tools. Luckily, these tools are kind of already connected to some of the ideas that you might already work with regularly in geometry processing. These ideas include variational optimization, which gives rise to Lagrangian mechanics, where we formulate physics as an optimization problem. And then we have symplectic geometry, which you can see it kind of as a cousin of the Riemannian geometry, where instead of having a Riemannian metric that measures distances, we have something called a symplectic form that measures a notion of area. And we also will use Lie groups, which is the natural language to describe the change of states in a lot of physical systems. And then this will give rise to a lot of symmetries and conservation laws. And these are what we're going to try to preserve. Okay, so here is the overview of our course. We're going to first give an introduction on the basics of Lagrangian and Hamiltonian mechanics. And then we're going to talk about Lie groups, symmetry, and reduction. And in the end, we're going to talk about how we can see discretization as a constrained variational problem, and how do we design algorithms that accurately preserves energy and other geometric structures. Okay, we're going to start with Lagrangian and Hamiltonian mechanics. Let's get into it. Let's try to have like a mental picture first. Imagine you want to shoot a cannonball. How do you shoot a cannonball out of a cannon? We know that when we want to shoot a cannonball, the trajectory probably wouldn't follow the blue trajectory or the red trajectory. It should be somewhat the yellow/white one in the middle. This is because its trajectory is not arbitrary. This is because it has to follow the principle of least action, meaning that the motion must follow a path of the least total cost. This cost is called the Lagrangian, and it is a function of position and velocity. And the optimal condition will give us our very familiar Newton's second law of motion, where F equals to ma. So what are the benefits of doing Lagrangian mechanics over Newtonian mechanics? For starters, when we're working with physical simulations in Newtonian mechanics, we have to keep track of all the forces, even though some of the forces might cancel out later. more importantly, Newtonian mechanics is coordinate dependent, meaning that if you want to perform a change of coordinate, you have to redo a lot of computation. However, under Lagrangian mechanics, even very complex systems with constraint, we can have a formulation that remains virtually the same. In fact, this is what makes it very alluring for us, computer scientists, because we now have a paradigm of constructing algorithms that are under the same principle. So, in a way, you can kind of see it as a form of object-oriented programming. Okay, so let's talk about Lagrangian mechanics. We need to start with our configuration space. We call it Q. What is a configuration space? Different systems have different configurations. For example, if you want to study a particle systems, the particle system is explained by their positions. So our configuration space Q is the space of the positions. Or for example, if you want to study pendulum motion, the configuration space is really just the angle. The tangent space of this configuration space is the infinitesimal change of configuration, which is, you can think about it as a notion of velocity. And then the Lagrangian is a function in the tangent bundle of the configuration space. It takes in a position and a velocity, and it's equals to k minus u, where k is the kinetic energy, which is 1/2 m times velocity squared, and u denotes the potential energy. The potential energy will depend on the specific problems that you're studying. For example, there's gravitational potential. If you want to study, like, for example, pendulum motion, there are other sort of potentials that happens between objects. I forgot what they're called, but it depends on the problem. Okay, and then we define the action. The action is the integration of Lagrangian along a path with the endpoints constrained. The idea is that we will optimize for a path to find the critical point of our objective. The action is stationary if its first variations are 0. Of all the paths a system could take between fixed start and end points, the one that it will actually take makes the action stationary. This is called Hamilton's principle of stationary action. This means that at every instant along the path, the Euler-Lagrange equation must be satisfied. That is, the time derivative of partial L over partial Q dot equals to partial L over partial Q. So Hamilton's principle of stationary action and the Euler-Lagrange equation can be seen as the same statement in two grammars. The first principle is a global condition on the trajectory of your physical motion as a whole, while the Euler-Lagrange equation is a pointwise criteria that you have to satisfy at every point in along your path. So note that when L is only the kinetic energy, it will define a metric on the configuration space. So then the Euler-Lagrange equation tells us that it becomes a geodesic equation on the configuration space. This is going to show up later when we talk about rigid body motions as well as fluid mechanics. Okay. Let's give like a very quick examples of what just happened. Imagine we want to simulate some pendulum motion. We have a pendulum hanging by a rope on the roof where the length of the rope is L, and then the angle is denoted by theta, and the configuration space is just a circle, and the position of your pendulum can be written down as L sine theta, negative L cosine theta, and the velocity is L times theta dot. And then we can write down the kinetic energy and the potential energy that comes from the gravity, and we can have our Lagrangian over there. So the Euler-Lagrange equation states that partial L over partial theta dot equals to ml squared theta dot, and partial L over partial theta equals to negative mgl sine theta. And this will give us the equation of motion, where we'll be able to get an expression for the acceleration of our angle, which equals to negative g over L times sine theta. So notice the quantity that's sitting under the time derivative over here is momentum. And we call this the conjugate momentum. So it turns out that we're going to use this momentum to move from Lagrangian mechanics to Hamiltonian mechanics. Okay, so just a recap, we have our Lagrangian mechanics, where we have our Lagrangian defined in the tangent bundle of our configuration space. And we're going to move into the Hamiltonian picture, where the important things no longer happen in the tangent bundle, but on the cotangent bundle, where the momentum lives. We're going to denote the momentum as P. So Lagrangian is a function on the tangent bundle. And using Legendre transform, we can transform Lagrangian into an energy in the cotangent bundle. And this is what we call a Hamiltonian. And now you can see that instead of, so you can see it equals to k plus u, while in the Lagrangian picture, the Lagrangian equals to k minus u. We also call this cotangent bundle the phase space. So this Legendre transform also shows up a lot in convex optimization. You might have heard it before when you're doing a variety of optimization tasks. Essentially, what it does is that it redescribes a convex function by the family of its tangent lines instead of by its points. Okay, so when we're moving into the Hamiltonian picture, the Euler Lagrange equations change into the following, where q dot equals to partial h over partial p, and p dot equals to negative partial h over partial q. So interestingly, you can rewrite this in a matrix form. And what this really is saying is that the evolution of P and Q, the position and the momentum, can be written as negative 90-degree rotation of the gradient of the Hamiltonian. So what this is saying is, if we consider how my P and Q wants to evolve under this energy H, it looks kind of like a gradient descent, but now we have it with an extra 90-degree operator J. And this J here is something called a symplectic form, and this is the essence of symplectic geometry. Let's make everything that I just said a little bit more formal. Let's formally define the symplectic manifold. We say a manifold is a symplectic manifold if it's a pair, capital sigma with little sigma, where the capital sigma is a manifold, and the little sigma is a two-form. So a two-form is something that takes in two vectors and it spits out a number. You can think about it as a way of some sort of area measurement. And there are two criteria for a two-form to be a symplectic two-form. First, it has to be non-degenerate, and second, it has to be closed. Intuitively, the first criteria, the non-degeneracy, later will let us talk about the Hamiltonian flow. And the second criteria over here, the closeness, is what makes a local canonical coordinate possible. Okay, let's talk a little bit more on the non-degeneracy condition of the symplectic two-form, as well as the Hamiltonian flow that it will give us. So sigma will give us a pair of musical isomorphism. Musical isomorphism is just a map between vectors and covectors, and then covectors and vectors. For starters, it will first define the flat operator. The flat of x is equals to, really, it's just if you insert your vector x into the first slot of your two-form, because two-form expects two vectors, you take in one vector, and now you're still expecting another vector, and now you end up with a one-form. And then you can take the inverse, and you get the sharp operator. And because the symplectic form sigma is non-degenerate, the inverse will always exist. And then we can say that the symplectic gradient of a Hamiltonian H is S grad of H equals to sharp of DH. So what this is saying is, so you have your Hamiltonian, which is a function. You take its exterior derivative, you get a one form. And then you sharp it, and now you end up with a vector field. And this is what gives us a Hamiltonian flow. In other words, the Hamiltonian flow is the solution to negative S grad of H. And here I have like a very small illustrations to just put everything together. You have your level set for your Hamiltonian H, and you see the red arrow denotes the direction of the gradient, and the S grad of H is a 90-degree rotation of your Hamiltonian, and then, of your gradient. And then you can see that if you flow along the direction of negative S grad of H, the Hamiltonian is preserved. Okay, so there is one important theorem that shows up a lot in symplectic geometry and Hamiltonian mechanics called the Liouville's theorem. What Liouville's theorem is stating that for any H, the Hamiltonian flow will preserve the symplectic form sigma. So what does this mean? This means that we can understand this through the following phase portrait. So we have this phase portrait living in the phase space, where this is a phase portrait of the pendulum example that I just included a few slides before. You can see this is a space of angle and momentum, and each curve on this phase space denotes a possible trajectory of the pendulum motion given some beginning criteria. And the symplectic form supplies the geometry that the flow must respect. For example, if you take like a small patch in your phase space, it consists of like some initial starting configuration that you want your flow, you want your pendulum to move with respect to. The Liouville theorem states that the Hamiltonian flow will preserve exactly the measure. So it carries the symplectic area to a symplectic area, and you can see that throughout the motion, the pendulum motion, this little patch over here is getting squished into different shapes, but the area is preserved. And this is precisely what Liouville's theorem is trying to say. Okay, so let's give like a very quick summary of what just happened. We talked about Lagrangian mechanics, which describes how physics F equals to ma can be seen as the optimization problem. And then we talked about how we can move into Hamiltonian mechanics under a geometric view using Legendre transform. So remember I said in the earlier that we care about the geometric structures that occurs in physical system, and we want to try to preserve these geometric structures. These geometric structures actually live in the phase space T star Q. And in the next section, Sina here will teach you about these fantastic structures and how do you find them and then preserve them.
Hey everyone. Okay, let's get into Lie groups. Let's see. Okay, what is available here? Right, so the next chapter that we're going to look at, and this is going to prepare us to finally get into the discretization world and constrained variations, is going to be this Lie groups, symmetries, and reduction. Many of the physical systems that we care about and we're going to study today, including the pendulum that we covered, the rigid bodies and fluids, you can see them, sort of their dynamics as being written as a change of variables between two states. One is the state that you start with, for example, the state at time 0. Let's call that space M, or model space. And its state at a later time t, let's call that W for world space. I did it M and W because we have this model and world in rendering as well. But the thing is that the map that lets you change between time 0 and a later time in all these different physics is some sort of a structure like this. For example, in pendulum, we have the circle group. In rigid bodies, we have the special orthogonal matrices, and in fluids, we have the diffeomorphisms that are actually volume preserving. But, and what they give us is sort of seemingly different equations of motions. Here I have something that Hesper showed us. It's missing its potential part because I'm only using the kinetic energy in the Lagrangian. And similarly here, I'm also just using the kinetic energies. But what is kind of curious to understand is that this right-hand side is 0, but for the rigid bodies and fluid, you see that even though I don't have any potential terms, the right-hand side is a non-zero amount. And my claim, or my promise, is sort of that we're going to learn that these three equations are basically structurally the same equation, even though they have very different, seemingly different structure. Okay, and just to see one thing also is that they are describing a change of the conjugate momentum, so this sort of hints us that we're going to see a lot of Hamiltonian mechanics showing up. Okay, so to do all of that, we need to go through a little bit into Lie group theory, and Lie group theory is a very deep topic, so we're just going to learn as much as we need, and we're going to use examples to sort of illustrate all the things that we need to know. So Lie groups are formally a group, G, that is also a smooth manifold, so it has two sides to it, such that its multiplication, that gives us another element in the group, and also its inversion, that also gives us another element in the group, they're both smooth. So an easy example is basically the SO3. These are these matrices that are also having their determinants 1. You can see that already that their multiplication gives you another element in the group. That multiplication is a smooth operation. And also their inverse is just R transpose, and that's also a smooth operation. So this is Lie group. There are other Lie groups that we care about. There are the SO2, the circle group. This is the group of all matrices that are invertible, because we need this invertibility to talk about Lie groups. And this is basically Rn together with the plus operation. That's also a Lie group. And so we're talking about manifolds and smooth manifolds. And if you've taken a course, the next thing we talk about is their tangent spaces. So their Lie algebra now, which is something that can be formally defined without the Lie group, is a vector space denoted by this math frac G that also has a bracket. The bracket has a few properties. It's bilinear. It is also antisymmetric. And it satisfies this cyclic property called the Jacobi identity. Now, an example of this is basically the matrix group. So you can see in the matrix group, if you have two matrices, we already learned that you can't multiply them in any order. So the bracket really measures how much AB times BA, AB versus BA are different. But okay, going back to Lie group, Lie algebra of a Lie group is actually its tangent space at the identity element. It just happens to be a specific Lie algebra. So for the SO3, we have this math frac SO3. This is the space of all skew symmetric matrices, and that's just one example that we should keep in mind. And this is going to show up, for example, in rigid bodies. So another concept that we're going to keep running into today, and we need to grab from Lie group theory, is how to act using Lie groups. So specifically, a left action of a Lie group G that acts on a separate manifold M is a smooth map that takes an element of G, an element of M, and returns another element of M. And it has to satisfy two properties. If you grab the identity element of the Lie group, it doesn't do anything to the element in the manifold. And then if you have two elements in the Lie group acting on the manifold, you can first put together those two elements and then act on the manifold there. So all this is saying is that it's really sending elements of the group into invertible transformations on M, and they also respect the product. This is useful because if you think of rotations, we usually understand rotations as they act on vectors. We don't separately understand rotations too much. We kind of understand them through their action on other vectors. And this is exactly what the first example is, the rotation of a vector in R3. But also, you can, if you want, basically multiply two rotations together. So if I have G and R, two elements in SO3, you can multiply them to get another rotation matrix. And there's one specific action that we really need to talk about to sort of like get into this physical understanding of systems, and that's the conjugation map. The conjugation map, again, sends G to G, but in a very maybe curious way. that first it does a G inverse, and then H, and then G. So it needs two elements, and it does this specific operation on them. So like for one, if you pass identity to it, because identity plugs in the middle, GG inverse is identity, so it fixes identity over there. But how do we kind of get a feeling for what this action does? Let's maybe look at this example. So let's say I have a vector in space W, and W space is, for example, the vector at, it's a space at later time t, and I said M is the state of the system as time 0. Let's say I have a vector here that I would like to rotate, but my rotation only exists in the space at time 0. How do I do this? So I can follow exactly what the conjugation does. I can grab that vector, apply G inverse on it, rotate it using that rotation H, and then plug it back in here. So I can do this sort of dance of going back, rotating, and putting it back into the space W. Or otherwise, I can grab this rotation, which is defined by an axis of rotation and an angle, and I can just basically push forward this vector using this G to go into the other space. And the angle remains the same. So these two operations are basically the same. And you can kind of imagine why this could be useful, because as we're doing physical systems, we're constantly switching between these two frames, the one that is sort of stationary or state at time 0, and then one that is at a later time. So again, because physical systems, you have both like sort of actions over time, and you have infinitesimal actions. So you can take this conjugation map, and you can take its derivative at the identity for its input. So when you do this, you take the derivative at the identity, you will see that now it becomes what is called an adjoint representation, sending Lie algebra elements to Lie algebra elements. To see this a little more formally is that you have to first define a curve H such that it passes through identity, and its slope at identity is some element in the Lie algebra in the tangent space there. And we're going to take its derivative at time 0. So this really just defines what is called the adjoint operator, given G acting on a Lie algebra element. And the point here is that what this does intuitively is that it carries one infinitesimal generator, this guy, and takes it from one frame and puts it into the other frame. So to see this doodle, let's do an example. So there's this hat map that we're going to need to talk about the matrices. What it does is that it takes a vector in R3 and it turns it into a skew-symmetric matrix. The way you can think about it is that every infinitesimal rotation can be given by an axis of rotation, and that's all you need. So A hat is basically a matrix, and matrices can be applied on vectors, which is basically the same as now a cross product between the two vectors. So that identity is what we need. And now we can also note one more thing. Rotation actually spreads over cross products, so that's GA cross GV. So now we can actually study the conjugation map, the adjoint map for matrices. Now, this one says if I want to send this A hat forward, what I can do is first take that V. Let's say this V is in the W space. I can look at its inverse, which is G inverse V. And then I can apply A. The applying of A is basically a cross product because A hat B is a cross product. And now that I have this, I can send this forward again. But when you send it forward, you can see that it's like applying G on this cross product, which spreads over it, and it becomes this vector that's over there. Okay, all this back and forth is a little bit confusing, so all you need to actually remember is that if you want to apply A and A exists only in M, you just need to push it forward using G. So you can do this much simpler by saying, okay, that's V. I'm going to push forward A, so it takes to be from A to that GA, and then I do the cross product. So again, this is another tool we need from the Lie group theory. But all these two actions that I just described, they're actions that take rotations to another rotation or infinitesimal rotations to another infinitesimal rotation. However, the physics, as we've learned today, they often happen on the conjugate momentum space, so in the dual space. Okay, I skipped one notation, so I'm going to go there. And so instead, it's better that we find the dual of these actions. So what we mean is that this one applies on G, the math frac G over there. But we can also ask, is there a dual operator, AD star, that acts on the dual space? To do this, we just need a pairing between these two spaces, a way of basically pairing them together. So by definition, AD star is the pairing that happens by taking this AD to the other side. And just to make it a left action, which means that it satisfies a few properties, formally the coadjoint action is defined as AD star of G inverse of 1, of G inverse. So I can explain this using another example. So for SO3 again, the pairing between two matrices, or a matrix and a dual element, is actually given through the Frobenius product, Frobenius pairing. That's this trace. So given that trace, we can identify elements of SO3 dual with also R3. So that just means that A hat, B hat, pairing of them is just a dot product of A and B. That's the identified vectors of the primal and the dual space. So this gives us a way of defining AD star. And that means that AD star of G, following through some operations, is just G inverse. But what we actually want is the AD star of G inverse, which is just G. So, okay, this is like a whole bunch of like magic trick of moving things around. What it actually does is that it says, if you care about in physics your conjugate momentum operator, which is a dual operator, you can take one and then just apply a rotation on it to get another conjugate momentum operator in a different frame. So from M to W, you can just apply a rotation. And formally, because this is called, this is the coadjoint action, the orbit of this action is defined at all the places that you can get by applying this action on one point. And because the action is just a rotation here, the orbit of it is this sphere. This is all the points that I can get from this initial point using an action that is just a rotation. And that is called a coadjoint orbit. So both of these actions that I talked about, the capital ADs, they have a sort of like a smaller cousin that is the smaller ADs, and I have to go back to explain that. The smaller AD is a second derivative of the conjugation. This time it says that if you remember, conjugation was GHG inverse, and now we're going to take its derivative on the G operator, the only thing that was not infinitesimal yet. And if you do that by associating that with a curve through exponential map, that is just going to give us, curiously, the Lie bracket. So it just says that if I differentiate conjugation twice in both G and H, I get back the bracket that was the Lie algebra bracket. So you can plug in two matrices. These are recording some infinitesimal rotations, for example. And this AD small operator just measures their commutivity. And through the hat map, that's just a cross product between them. So this is also can be done in the infinitesimal sense. So you can have like the AD star also show up as the dual of AD. And this one shows up here now. So AD star of a matrix applied on a dual conjugate momentum is also just a cross product of these two vectors. The reason I'm showing this is because you can see that this is the infinitesimal coadjoint action, and it's basically just a cross product. And you can see this in the Euler equations for rigid bodies. It's the conjugate momentum I omega cross product the primal element here. So really, it's saying that the change of this momentum is equal to an infinitesimal coadjoint equation. So this is sort of a hint that we're going to run into this. So these are the actions of a Lie group. They're a little bit, interesting to learn about. But what we want to take away from them is also this important concept, that if I have a manifold M and it has a structure, it could be a function, for example, the Hamiltonian. It could be the Lagrangian. It could be a metric that I have on that manifold because it's a Riemannian manifold, or a symplectic form because it's a symplectic manifold. Any action that I apply on M such that it does not change that structure, the structure remains invariant, that's called the symmetry of that action. So for example, in energy, we could assign a function to every point of the manifold and apply an action that basically doesn't do anything to that energy. If you do the same thing with a metric structure, that is called an isometry. And if you do the same thing with a symplectic form, you can call that symmetry a symplectomorphism. So some of them are so common that they have a different name and not called symmetries. But in physics, symmetry comes as a very, very deep topic, and this is due to the celebrated theorem by Emmy Noether that says that for every symmetry that you figure out in your system, let it be fluids, rigid bodies, or whatever, you will get a new conservation law. So the most common one that pretty much all physical systems have, if they're conservative, is that if you do your experiment today, like for example, if you shoot a ball on the pool table and you do it tomorrow exactly the same way, nothing changes between these two instances in time. So this symmetry in time gives you a conservation of energy. And you can do the same argument for translation symmetry, again on the pool table, so there is a linear momentum conservation. And same thing for rotations when it comes to rigid bodies. And some other ones for electric charge. But most importantly today, I want to talk about this one. Fluids also have a kind of a non-trivial symmetry, and it goes something like this. So imagine you have a continuum system of fluids. You can think of them intuitively as a infinite number of particles, like a lot of particles. And you can label these particles from 1 to the biggest number we know, like infinity. And we can pour the water out of the cup. And then we can now rerun the experiment, so put it back, and then shuffle those labels on the particles, and then pour the water out. The way you label these particles have nothing to do with the way that the water pours out of the cup. So that is a symmetry. And that symmetry, by Noether's theorem, has to come with a conservation law. And that is called the conservation of circulation. So we'll get into this a little bit later when I talk about conservation laws a little more. But roughly speaking, that just means that for us computer graphics people, that means that the vertical details, like all those little swirls of the smoke, should be preserved over time. But okay, if I have a symmetry, what else can I do? Because, for example, the Lagrangian is invariant under some of these symmetries. And remember, when Hesper was talking, Lagrangian is the way we run up that optimization variational system to find out our Euler-Lagrange equation. So if there is a symmetry in the Lagrangian, that just means that there's a symmetry in the action, so the entire variational principle has a symmetry. And that just means that some of the configurations are redundant, and we can remove them. So formally, it means that this LQQ dot, you can put one of these phi g's and it doesn't change it. So we're going to quotient out these redundant directions, and that is what is called the reduction in Hamiltonian and Lagrangian dynamics. What happens is that we can replace this entire QQ dot with whatever variable that explains the system without all the redundancy. Let it just be called U. And then we can define a reduced action based on the reduced Lagrangian. And we're going to run the same variational principle of stationary action on this reduced thing, because we managed to remove all the redundancies. But we run up to a small issue, and that's that when you are trying to reduce these variables, you have to be careful about one thing, because when you didn't reduce them, you were able to test it against all possible variations. But when you do reduce them, there is sort of a change of variables relationship between the reductions, between the reduced infinitesimal variation and the variations that are reduced. So it's no longer just delta omega is eta dot. That's sort of like before we saw this as delta q dot. But it gets a new term, namely this small AD operator that is a Lie bracket. It kind of needs to measure how much does the reduced variation commute with the infinitesimal reduced variations. And this is formally called Lin constraints, and we can go over this more in detail on how it's proved over the coffee break or the lunch break. But what it does for you is that it induces a constraint now on the variational system. So you can't just sort of run it with any variation. And what that does is you get a new term. So this is where that new term comes from whenever you don't have a potential energy. You get one extra term that is this AD operator. Somewhere else you might have seen this if you have seen material derivatives in Eulerian and Lagrangian coordinates. This is basically a statement on the opening up that material derivative and writing things in Eulerian coordinates. But maybe more to our point of this course, this little guy here, that's exactly the conjugate momentum. And just like Hesper did, I can also write this as a negative S grad of now a small h, a reduced Hamiltonian. So this is also a symplectic gradient descent that is happening here. But there's a catch. Because I reduce things, there's new things showing up, which means that when I'm talking about Hamiltonian dynamics, the phase space is now called a reduced phase space. And specifically, the phase space is a dual of a Lie algebra. It's this G star thing. And G star is a new space that is related to symplectic geometry. It's called the Poisson geometry, or Poisson space. This space, basically what it comes with is that it is a larger class of symplectic spaces, and it comes foliated with submanifolds of symplectic spaces. That is really due to the degeneracy of that S grad. So there's some direction that this S grad, you can compute it, and it spits out 0. So those directions are exactly the directions orthogonal to these submanifolds. But when you evaluate it inside the submanifold, you're able to actually move around. And this is the complete picture of how reduction really takes you from spaces that you could previously, like the phase portrait of a pendulum, you can move anywhere inside of it, to places where you have to be stuck onto a submanifold of these spaces. And these symplectic manifolds are actually coincide with the orbit of these coadjoint actions. Remember that sphere that I showed you? That is like a more abstract doodle of that. And it's even better. On every one of these sheets, you will get a conserved quantity, and that's a Casimir. So basically, this is formally saying that Noether theorem again. You have a symmetry, you're able to reduce things. When you reduce them, you get a coadjoint action, and it has an orbit that is in this space, and it comes with a conservation law. So this is sort of like a geometric worker, like a picture of Noether theorem. And yeah, so Casimirs are quite important. And one statement here is that the Casimir of a rigid body is the conservation of angular momentum. Okay, so I'm just going to quickly tell you that once you understand things in this picture, it's like you kind of invest in like something hard to learn, but it pays off. Why? Because now you can basically choose your configuration space, but the entirety of the machinery remains the same. So for the rigid bodies, you can choose SO3. For fluids, you can choose volume-preserving diffeomorphisms. One of them, you get rotations and infinitesimal rotations that are skew-symmetric matrices. The other one, you get flow maps and divergence-free velocity fields infinitesimally. And then you can look through your actions. So we have the big AD, which is the adjoint action. That was a rotation in the Lie groups. It's a push forward on the fluids. The small one is a cross product for rigid bodies. Now it's just a Lie bracket of vector fields on the fluid. The dual elements, it's just the momentum, angular momentum. Here it's a covector or a momentum. AD star, the one that we really care about, the coadjoint action, is a rotation here. For fluids, it's a pullback. And AD small star, it's a cross product for rigid bodies, and it's a Lie derivative for fluids. So if you just sort of like even use this as a lookup table, you can say that, okay, the rigid body dynamics has to be equal to a coadjoint action, which is a cross product. I look it up here. And then the ideal fluids, the coadjoint action, has to be a Lie derivative, so it shows up there. This little extra term is just because we have a constraint of volume preservation. But otherwise, this is the equation, which just this operator gets replaced by the Lie derivative. So I think what we have done here is that we show that there is a general recipe of studying physical systems that can be somehow put into this machinery of Lie group theory. And we give two examples of rigid bodies and fluids. And interestingly, even the pendulum counts as one of these, except that its Lie bracket is 0. So it's like a very trivial example of a Lie group. And maybe it's worth to like see a little more as example of fun things you can do with this picture in mind. Will display? No. So this is, just to get a picture, this is what rigid body does when it has no gravity acting on it. So this is completely, you can say, inertia driven and kinetic energy. So you can say that because it's an S grad motion, symplectic gradient, it will preserve the energy. And also it has this other angular momentum level sets. These are the coadjoint orbits. And the dynamics is this 1D curve inside at the intersection of these two. So this is the ultimate way of getting reduction. You started with a state space that was completely in the 3D space, and now you're guaranteed that your physics should be a 1D curve inside of this 3-dimensional space. And you should hopefully have a numerical simulation that can actually respect this intersection. And that's what all these geometric numerical integration courses are about, to do symplectic integrators, to do Lie group integrators, to really capture this picture discretely. And once you do, as Henry Casimir said, you will get that your angular momentum is conserved on these things. And this is just to recap it for fluids. This is a different now conservation law by Kelvin and Emmy Noether with the particle relabeling. And you can do a similar reduction. So you go from the big space of Lagrangian description of particles with position and velocity, and you go only to Eulerian description where there's only velocity or covector velocities. Oh, I do have U flat for the university. And this gives us the coadjoint orbits of the fluids intersected with the energy level set. And so the motion should be at the intersection of them. This one is not as simple. This is not like a 1D curve because the state space here is actually infinite dimensional. And the submanifolds are lower dimensional, infinite dimensional stuff. So I think most of the geometry people say that we're not going to deal with that. Okay, so another name for this reduction map is called the momentum map. That's something that we're going to use later. But so one question is, I told you for the angular momentum, these are labeled by Casimir's of angular, like value of angular momentum, but what is it for fluids? So for fluids, I just have to iterate that for ideal fluids that are incompressible and inviscid, this conservation law that we're going to talk about is going to be really what sets us to preserve these nice vertical dynamics. So it's like in graphics point of view, this is exactly what we should do. And that conservation law is due to Kelvin. It says, it's very fun. It says, pick any curve, whatever curve you like, that it should be closed, and measure velocity integrated along this closed curve, and let it flow. And strangely enough, the value you measure at time 0 or at any later time, they're exactly the same. And this is not for any specific curve. This is for any closed curve you pick in your domain. So why does this make sense? So in the 2D sense, think of the Stokes theorem that if you take the integration on a closed curve, this is related to the integration of curl inside the closed curve. And that kind of tells us that the 2D vorticity information is completely conserved inside of this little loop. And hopefully you want all information, as long as it's related to vorticity, to be preserved in your simulation. In a more dimension agnostic way, Helmholtz said that in general, vortex lines are transported by the flow. So you can imagine that you have some sort of vorticity forming along like your plane wing, and this, if it's ideal physics, this vortex line just gets carried by the flow and it doesn't dissipate. So this is where things get into topology and topological hydrodynamics, because that statement can be made into a function, which is what Casimir's are. And for 2D, that just says any function of vorticity is preserved. That's countably infinite many functions. And for helicity, for 3D, it's just one. And it's basically saying it's a dot product of velocity and its curl vorticity. And if you've seen this maybe in other places, this is basically the average linking number of the vortex field So this little curl U. And that's why, for example, if you're having an initial configuration that looks like a knot, the average linking number of this guy will be preserved as it's moving with the flow, with fluids. So that's how you label each of these sheets in 3D with the average knottedness and that with the functions of its vorticity. I'll show you like two simulations. So this is a vorticity field that's initialized as a Trefoil knot. So as it evolves, like our simulation captures this very well-known event that's called the separation event in very, very high Reynolds number with very little viscosity. And you can see that it's not really losing its vorticity as it moves. And this is called an unknot. This is a curve on a torus. And these are all also under very low resolution. And it also has its own curious separation event. So we can do these kind of cool things if you really pay attention to the structures that you care about. But okay, how did I actually achieve this, and what is the math that goes into actually discretizing these things? So for that, I have to talk about how to put constraints on our variational problems. So our variational problem, which was this least stationary action principle, was unconstrained, except the reduction. But maybe I can put some constraint on it. For example, I can say that in this pendulum, the length is fixed. That was also built into the configuration, actually, because we just had theta. Or it can be that this helicopter should be not hitting this obstacle. So that's a positional constraint. Or we can say that the flow should be volume preserving, which is the same thing as saying that the flow should be divergence free. Oops. So all these constraints, they're called holonomic constraints because these are constraints that are only involved on the positions between the two variables that we put into the Lagrangian. And even if it is divergence-free velocity constraint, you can integrate it into positional constraints. But there are constraints that you cannot integrate from velocity to position, and they sit on velocity only. This is like when you're driving your car, or you know how to do the snakeboard. And this basically says that when you're navigating these vehicles, you can only actuate it in the direction of the wheels. So that becomes a non-holonomic constraint. Or you have these examples with a ball that is rolling without slipping. So if it needs to roll forward, it needs to, its angular velocity needs to match its flat velocity. So how do you study these systems that have non-holonomic systems? Because if they have holonomic systems, like the pendulum, you can just change the configuration space so you don't even see the constraint. But you have to deal with these non-holonomic systems. And just to recap, one of them is integrable, one of them is not. It looks like this. So let's just put it to the test and do a rolling ball without slipping. And let's say I want to deal with non-holonomic constraints. The typical way that people do this is through the Lagrange-D'Alembert principle. This one says that there's going to be a kind of a virtual force. There's a force that's imaginary, and it's going to make sure that the constraint is satisfied. And that force is applied after I take the variational optimization. So I take my variations, my least action, without assuming there's any optimization. Without assuming there's any constraint, and then magically later I'll add some forces to add those constraints. This feels a little off, but it generates the right physics. Now this one, if you look at it at the end, it sort of spins a little extra compared to this one. It's as if like it's trying to move and then there's one extra twist at the ends. It's almost as if there's a little hamster inside the ball that's making sure that the path is very optimal. So the way that this one is done is that its constraints are done through the method of Lagrange multipliers. So this is completely a variational optimization. And it has a funny name. It's an acronym that is called variational axiomatic kind of non-holonomic systems. This was just to hammer in that this one is not variational and axiomatic, but somehow it does turn out to be what our physics look like. So most people defer this to optimal control directions only. So whenever you actually have a hamster sitting in your ball, or like a robot that's controlling your optimality, you should use Vaconomic principle, which makes sense. So which one should we use? when we have discretizations. So when we want to discretize physical systems, because the space of velocities that we care about in fluids is infinite dimensional, because it's a continuum, we have to choose how to deal with this constraint that is the velocity, like discretization constraint. So this is the space of all discrete velocities, and with an interpolation function, you can place yourself into the space of all velocities. But you can't possibly represent everything. Think of frequencies, like you only have access to frequency 10 or not higher. And you want to be able to still, for one, even though it's finite frequency, still have this divergence-free constraint satisfied, but also be able to say similar things that you could say when you were not constrained to just limited frequencies. So how do we do this? This kind of makes our configuration space look like this, actually. So what it does is says that if I'm at a certain configuration and I want to start moving, I can only move in the spaces of discrete velocities, in the directions that my discrete velocities allow me to move. So if I want to find the geodesic between 2 points in the space, I kind of have to find a curve that satisfies the infinitesimal constraints at every single point. This is not your normal geodesic of the Riemannian geometry. This is, so that would be like the straight line. This is what is called the sub-Riemannian geodesic. It's the optimal path that satisfies a set of constraints. And discretization should be viewed as such a constraint. So if we understand it with this picture in mind, and we kind of like observe what other people do, what most other finite element methods do is that they say, okay, I'm in the space of all discrete velocities. I don't need to consider whether this is a constraint in all the possible velocities or not. I'm just going to write my entire system in this dual space, the discrete dual space. But the discrete dual space is no longer a Poisson space because its primal one is not a Lie algebra. Not being a Lie algebra means that if you take two elements in this subspace and you commute them or measure their commutation, it leaves the space. So you can't have those structures of Kelvin circulation and coadjoint orbits. But they do exist here on the continuous dual space. And what you can do is just do something really quick, which is define your Hamiltonian in your discrete space and then pull it back. So what this defines is now a discrete Hamiltonian that the grid can measure. The grid can see this Hamiltonian. That's why it's actually coming from here. But the structure, the S grad, and like all those symplectic Poisson, all the ways that Hamiltonian mechanics works, still comes from the continuous space. So this gives us sort of a filtered Euler equation, which we call I-discrete Euler equations. And this filtering comes on applying basically a projection on the velocities that are used in that Lie derivative for transportation. So a higher frequency velocity or momentum is carried by a lower frequency field that is projected. And it turns out that this is the least intrusive way of changing our equations so that we can simulate them on a computer. Because the I-discrete flow preserves the energy of this new energy, and also it doesn't interfere with the coadjoint orbits. The blue sheets are exactly the same between these two formulations. But if you compare this now with the previous finite element methods, previous finite element methods and the way we generally deal with physical systems when we're talking about simulating them, we don't care about the coadjoint orbits too much, specifically for these infinite dimensional systems. They're just out of our hand, and mostly we basically say that, okay, as long as I am preserving the energy, which is something I can measure on the discrete sheets, like this green line, I should be fine. But that's not the case, because if you do this, you're following that Lagrange-D'Alembert virtual force system, and that will not give you geodesics, that will not give you a variational system, and it will also not preserve any coadjoint orbits because it knows nothing of these sheets. It only knows of that blue discretization subspace. But the other way, like this middle one, it gives you sub-Riemannian geodesics, vacuonomic principles, and also coadjoint preservation. So you should take this as a new Euler equation, like a modified Euler equation that we're going to aim to solve. This hasn't been completely solved yet. So how do we solve this? To do this, we need to, again, use some geometric insights. We're going to prepare some other auxiliary symplectic space that this time, this is numerically tractable. It's unlike that one is not infinite dimensional. And then we're going to use this concept of momentum map. This concept tells us that whatever happens here is exactly the same as this. It makes sure that the physics are the same. But this is not a hard thing to achieve between two spaces. Because you can say that if the primal space of this guy acts in a way that is preserving the symmetry of the symplectic space, so it's symplectomorphic, this thing is canonically defined. You can look it up in a textbook, basically. And this now establishes that whatever you do here, which is importantly numerically tractable, is the same as this guy, which is numerically intractable. And now, so what do we do? What spaces can we choose here? We can choose, for example, Clebsch variables, point vortices, or more classically, just a bunch of particles, position and momentum variables. So we choose the last one, which is this is the most generic one. And we show it as a system of particles. So together, this places us in a hybrid situation between grid velocities and particles, which we call the co-adjoint orbit fluid implicit particle. Fluid implicit particle is the most common method in computer graphics for dealing with fluid stuff. And this equation of motion is now basically summarized in this kind of diagram. So you do a momentum map to go from particles, and you go to this equivalent dynamics in the dual space. You kind of project yourself back, filter the velocity, and then you do an advection using this phi star. We can talk about this over the lunch break as well, but the point is that because every single thing we did was respecting the structures that existed in the continuum world, and we only surgically changed things that doesn't mess up with the conservation laws, because the conservation laws were attached to these blue sheets, and we only changed the energy. We're able to have all of these things conserved. Formally, that we have a Lie group integrator. The transfers between the particles and the pressure projections are very canonically defined using that interpolation operator. And we have a Hamiltonian ODE that we're solving. So this system remains a Hamiltonian system. So there is no numerical diffusion here. And removing numerical diffusion is an important task to achieve for accurate simulations. So what does this let us do? So for example, a few years ago, we had this paper, co-vector fluids, and we were able to achieve these things with pretty high, I mean, for me, relatively high resolutions. With this work, the co-flip paper, we can achieve these sort of like very highly turbulent motions with much lower resolution. And you can even go lower. So this is half the resolution of the co-vector fluid one. And this one still has all these structures forming. So the important thing is that even though we're reducing the resolution, that's only affecting the energy. All those sheets are still there. So all your structures, the things that make you look like a fluid, are still present. You can see this even easier in this example. This is just two vortices keep leapfrogging to each other. These are all the previous methods. And really what you need to see is that the vorticity should be preserved. That's the measure of you staying on that co-adjoint orbit. And you can see all these previous methods are quickly losing their vorticity over time. But the one that aims to preserve it does preserve it. And that goes on and on. Just going to go to the next slide. But yeah, so it can also let us do fun things in computer graphics. It's not just about numerical simulations and accuracy. And hopefully more people will try to utilize this point of view and get their simulations more accurate and also more good looking. So in terms of conclusion, structures such as symmetry are essential for physics, and especially physics that are conservative, such as ideal fluids and rigid bodies. Discretizations generally benefit from like this variational non-holonomic constraint system that we treats the constraint as vacuonomic systems, not the Lagrange-D'Alembert virtual force. And also, well, similar to geometry processing, if you respect the structures that exist continuously, you will gain a lot of benefits. So thank you, and we'll be happy to tell you about the questions. And just to let you know, both me, I'm going to be on the faculty job market this coming cycle, and Hesper is going to be on the postdoc job market this coming cycle. So hit us up if you have any positions available. Thank you. Okay, hi, of course, David.
Okay, thank you, Sina and Hesper. So you mentioned earlier that this vacuonomic dynamics does not give you the correct physics in certain situations. But then later on you said that what's great about this method is it gives you vacuonomic dynamics. So can you say more about that distinction?
Right. So it really depends what kind of non-holonomic constraints enter your system. So when you're talking about sort of natural world where there's no discretization, there's no simulation, and you have a constraint such as this rolling without slipping, that is like a sort of a friction force. And friction forces don't really naturally they're not accounted for in our Lagrangian and Hamiltonian systems. So it doesn't too much make sense to say that they should be treated as a variational constraint. They're actually the thing that should sort of, come in after the fact. This is sort of like a bug with our mathematical modeling of the Lagrangian and Hamiltonian worlds, because they really take care of conservative systems without any constraints. But on the other side, the simulation world, the non-holonomic constraints doesn't come from friction or something sliding over something else. This is just because we have a discretization. A discretization itself imposes a non-holonomic constraint. And the question is, how do we deal with this non-holonomic constraint? Do we deal with it in a way that forgets about the structures and conservation laws that we care about, or do we account for them as well? Yeah.
Okay, thank you.
Of course.
Hi, thank you very much for thank you very much for the presentation. First, I want to say that the Koflip paper was probably the most impressive paper I've ever seen in the graphics community. So congrats, it's really insane. I had a question about when you speak about the fact that you end up with a modified equation that is adapted to the discrete setting. And I was wondering what kind of control do we have besides this discretized version and the continuous theoretical Euler equation? Do we know that your modified equation will converge to the Euler equation under refinement or that kind of stuff?
That's a good question. I think we didn't formally study this when we wrote the Koflip paper, but I think this, there have been over the history of I think the past 100 years, other people have come with other filtration ways of modifying Euler equations, and most of the other filtrations have good convergence behavior, and this one seems intuitively, it just says that you're kind of filtering that velocity to be into a finite element space, and most finite element spaces have nice convergence to the continuous behavior. I don't know, but I feel like it should be good, and if not, it's a good direction to look into.
Okay, thank you. And I just had one quick other question. When you speak about numerical viscosity, did you mention that you suppress them completely, or is it still remaining somewhat?
For most intents and purposes, as long as you can compute a flow map computationally, so this is the key point here, you need to be able to compute these invertible diffeomorphisms between every two frame. So as long as you can compute that, there's no place in this scheme that introduces numerical dissipation. Okay. But with that comes a strong caveat that now you can't make any bugs. You can't make any sort of mistakes, because now you have to take care of this possibly, because there's all these laws called the cascading laws, and there's a lot of, naturally the system wants to get more and more fractal shaped and more and more detailed. So you need to be able to resolve all those very, very small flow maps. So up to that constraint, you will not have any numerical diffusion. But once in a while, we have to reset these computation of these flow maps to just make them simpler again. And that resetting will involve a little bit of numerical dissipation.
Okay, great. Thank you.
Yeah, of course.
So you mentioned that you could set up your coadjoint orbit scheme on top of like whatever your favorite method of fluid simulation is, right? You chose flip, but you said you could have chosen Clebsch variables or point vortices. How much work is it to take one of these other schemes and make the co-version of it?
Yeah, that's a good question. Really, it amounts to sort of like how comfortable you are with the other systems. Let's say like, so for example, for point vortices, it's rather simple because all it does for point vortices is that it makes your simulation, like your scheme, strictly simpler. Your particle to grid transfer becomes like just sort of like a summation in some part of the code. So that's really, in that sense, it's very easy. So I don't know, in my head, I see a future where you kind of have almost like a compiler version of this thing, and you swap between your favorite configuration spaces or auxiliary symplectic spaces, and you have all kinds of physics, all kinds of choices within every physics, and that could be fun to do. Yeah. Yeah. Thanks for the question.
Well, if there are no more questions, let's thank the speakers again.
Thanks.